Okay, to solve this problem, we first have to draw a rigid body diagram. And so what we have is we have a rigid bar and its mass acts at the center. So I'm going to draw that as a force acting downwards. And I'm going to have to call the mass of the bar m sub b. And then there's a weight hanging 3/4 of the way down, and that's going to be here. So there's a force acting here, and that's mg as noted in the diagram. So we got to stick with m for that one. There's a tension which acts, and that tension acts at the end of the bar, and it acts at an angle something like this, and I'm going to call that tension T. And then right here where it's attached to the wall, there's got to be some forces on it there, so I'm going to draw them as two separate components. There's some force pushing on the bar in the x direction. I'll call that F of x. And there's probably some force pushing up at the wall. I'm going to call that F of y. So there's probably some force pushing up at an angle, but it has components that look like that. Now, the thing you got to watch out for is this angle here is not given to you in the problem. I give you the problem that this rope makes with the wall, and so you got to use a little geometry to figure out that this angle is the complement of that. So if that angle up there is 60 degrees, you're going to be using this angle down here, which I'm going to call alpha. And you're just going to have to remember that the angle alpha is not theta. It's actually 90 minus theta. Okay, so the easiest way to solve this problem is to start by making this point over here the pivot. So I'm going to make a little dot here and label it P. And then I can state that the sum of all the torques about point P have got to add up to 0, because this bar is not rotating around point P. If it's in static equilibrium, it's not rotating about any point, including P. Okay, so now we got to figure out what torques there are about point P, which forces tend to rotate this bar in that direction, and so that's T. So the positive torque is going to be T times the distance at action, the pivot, which is L, times the sine of the angle between the force and the radius, and that's going to be alpha. So that's the positive torque. We're going to have a couple of negative torques. The mass of the bar, when multiplied by gravity, gives you a force, and the distance that force action, the pivot, is L over 2. And then the load itself, mg, acts a distance L times 3 over 4. So the sum of all the torques have got to add up to 0. And so what you'll notice then is that the L's cancel. And once you cancel the L's, you know everything else except the mass of the load, which is, I think, what you're trying to find in this case. Oh, I'm sorry, you're trying to find the tension T. So you're trying to find this tension T. So you can solve this. You know theta, so you can find alpha. You know the mass of the bar. You know the mass of the load. You know G, so you can solve this. So I'm going to leave it from there. So let's assume that you can now solve for T. Now, part B of the question asks, what is the horizontal force applied on the beam from the wall? So we're basically trying to find F of x. So this is actually, you can't really use any point on the bar as a pivot, because F of x goes straight through the bar, so the radius will always be 0. So the easiest way to solve this is to think about Newton's laws. The sum of the forces in the x direction have got to add up to 0, because it's not moving in the x direction. So what that tells you is that the force to the right, F of x, minus the force to the left, which is the component of T going this way, so that's cosine of alpha, that has to equal 0, and since you found T in part A, you can find F of x. And then lastly, if you add up the forces in the y direction, they also have to equal 0, and that will give you an expression that you can solve for F of y. Okay,